Okay, so the first thing that we are going to have to do on this one is we need to come up with a statement. Now, just curious, how many of you guys just said that we had two congruent triangles? How many of you guys made a congruency statement about different parts?
I did.
Who made a congruency statement? Wow. Okay. Thanks for listening. So, on here, we could have said that we had two triangles that are congruent. Now, looking at it, hopefully you can identify which two you think might be congruent. Do you see two large overlapping triangles here? Yeah. So there's two large right triangles that are overlapping. Those two triangles, so essentially triangle HJK and triangle MLJ, those we could prove are congruent. Now, we could go even further than that. We could even prove parts. So I'm going to take this a step further. I'm going to start off by saying I want to prove that these two hyponi are congruent. So we have HK and MJ. So we are going to prove that HK is congruent to MJ. Now, if that's what we're trying to prove, when we do our proof, what would we call this for our proof? That would be our, well, not our given. It's what we're trying to prove. It's our proof statement, right? So on here, I could say that this is what I'm trying to prove. Now, givens. What's actually given to me on this problem? So I know I didn't have the givens listed, but there's a diagram with lots of marks on it, right? So what do we know based off of those marks that are already on here? All right, so HI, you said, right? HI is congruent to ML. And that's already marked. So these two are congruent. Now, we also should know a few other things. What else is already marked for us? Anything else? JN and KN. All right, we can go with those. JN is congruent with KN. What? One more thing that was given to us.
All right angles are.
Now, I agree with that statement. All right angles are congruent, but was that what was given to us?
Well, there's two angle eyes and angle L.
Well, okay, you gave me the statement that she was giving a reason for it. You said angle I is congruent to angle L. That's not what those mean. So take a step back. We only know that they are right angles. So that's what's being given to us. Angle I and angle L are right angles. Okay? So now we know what's given to us and we know what we're trying to prove. We can write ourselves a proof. So first thing that we're going to do, draw our two columns. We have our statements. We have our reasons. Now, we could easily start off with that first given, right? So let's start with that first. HI is congruent to ML. Why? Why? It's given. Now, based on that given, do we know any other information? Based on that given statement, do we know any other information? No. Knowing that those two are congruent doesn't tell us anything else right now. So, we got to move on to the next thing that was given to us. All right? We have JN is congruent to KN. And that's given as well. Now, does that tell us anything else? I think it does. What you got? All right. How did you know that? So angle J and angle K are congruent. J congruent. Ooh, hold on 1 second. I'm missing a step. I like it, but we got to figure out how we got there. So how did you know that?
Because of the theorem that states that the opposite angles are congruent.
Okay, so if two sides are congruent and the opposite angles are congruent, when is that true? Because that's not true in any figure. It's a specific type of figure. All right, so that was our isosceles triangle theorem. So what you're telling me is that we have an isosceles triangle, right? So the first thing that we'd have to say here is, hey, see this triangle in the middle? We know these two are congruent, so by definition, this is an isosceles triangle. So we can say triangle NJK is isosceles. If you wanted to be even more specific, you could say something about like with a vertex at N, because then that tells you exactly how it's isosceles, which parts have to be congruent, and so on. All right? So we know the statement because of the definition of isosceles. So that's what our reason would be. Definition of isosceles triangle. Now we can put that next piece, right? Because now that we know we're dealing with an isosceles triangle, you had said angle J is congruent to angle K. And why this was important to us, the two parts that were marked congruent here, those aren't actually any of the sides or the angles of the triangles we're trying to prove are congruent. But these two angles are. That angle's in this triangle, and this angle's in that triangle. Now, I do have one problem with our statement. All right? There is one problem with this statement. Can anybody tell me what's wrong with it right now? Because we do need to fix it just a little bit. Which angle is angle J? This one?
No.
This one?
Yes.
Okay. Well, how do I know I'm talking about that one and not this one?
I'm not sure.
Because it has a line.
No.
Well, we know that that's the angle we want to mark as congruent, but is that what this is saying? Is this telling us that we're specifically talking about that angle?
Yes.
If you have more than one angle coming off the same vertex, how do you have to name it? Can you just use one letter? All right, NJK would be more appropriate. So if you can squeeze it in there, great. You need to move your angle symbol a little, whatever, but NJK, we need to use three letters because we could be talking about NJK or NJI if we just said angle J. We could even be talking about the straight angle IJK. So there's three angles using that same vertex. So again, if you have more than one angle on that same vertex, you have to use those three letters. All right. Same thing over here with angle K. So instead of just saying angle K, we could go NKJ. Now that's a good statement. So these two are congruent, and you already said why. Do you remember why? So that's our theorem. And then I don't know who else said it. Somebody actually said the name of that. What was the name of that theorem? So it was based on the fact that we have an isosceles triangle, but it's not the definition, it's the theorem. So isosceles triangle theorem. All right. So the definition tells us we have these two sides are congruent, therefore it's an isosceles triangle. The theorem says since we know it's isosceles, the angles across from those two congruent sides are also congruent. So now we could mark these two pieces. I'm going to mark them with pencil because I want to erase this. We could say that those two angles are congruent. And that's going to help us in this proof, because now we have two parts in this proof listed as congruent for the figure. That first one and this last one. Now, there was one other given statement that we haven't used yet. What other given statement was there?
The angle thing.
Okay, so angle I and angle L are right angles. Again, that too was given. So now we've used all our givens. What do we know because of this statement? So we already said this. I'm trying to remember who said it. Somebody originally said something else about our statements. Instead of saying that these were right angles, you said that they were congruent. So on here, we can say that angle I is congruent to angle L. And we knew that because, what's the reason there? Again, somebody else said this. I don't remember. That's what.
All right angles are equal.
All right angles are
Or congruent.
congruent. All right angles are congruent. And again, that's the whole thing. So you just write that one out. There's no specific name for that one. But now we have three parts congruent here. We have this angle, this side, this angle, and this angle over here. So what statement could we say now? So now that we have three parts congruent in both triangles, what comes next? So once you know we have three parts congruent in the two triangles.
Or hypotheses.
Okay, so you guys are listing some theorems here. What are you trying to tell me about these theorems, though? What statement are you making? The what? Okay, so we're using congruency criteria. These two triangles, our statement will now be the two triangles are congruent. So we gotta say which triangles. So let's say we said triangle HIK to start off. Now, everybody's statement here could be slightly different, because depending on what triangle you were trying to prove congruent, you could label it differently. Again, this statement, if you were having your proof statement be a triangle congruency statement, you'd have to match whatever you had for your proof statement. So now, I'm saying triangle HIK is congruent to triangle what? Because now we have to go in corresponding order. MLJ. MLJ. Now, that last reason. So, what pieces do we have congruent in those two triangles? All right. So those were angles, right? So we have one set of angles. Do we have any more angles? I and L. So we have two sets of angles. Do we have any sides? Yeah. HI and ML. So we have three parts. We have two sets of angles and a side. Now, is the side that we had between the two angles or not between the two angles? So if we just look at one triangle at a time, let's focus on this guy. We have this angle, and this side. Is that side between these two angles? No. So which one is it going to be? What was it? SAA, or you could say that the other way around, AAS. So either of those work. So either AAS or SAA. Again, those two are the same thing. Two angles, a non-included side. Now, if you're just trying to prove triangles were congruent, we'd be done. But when I wrote out, we went one step further. So this has to be my last statement. Now that we know the triangles are congruent, can we say that these two hypotenuses are congruent? Yeah. So the hypotenuse of both triangles are congruent. Why? CPCTC. So again, that was a much harder proof. We brought back a lot of other concepts that we hadn't done in a proof yet, including some of the things from earlier in this chapter, like isosceles triangle theorem, the definition of isosceles triangle. We did have all right triangles all right angles are congruent in one of our proofs from this section. So again, there's a lot of different ideas here that come from earlier in the section. Now, could we have done this in different order? Yeah. But the order I did it in this order to try to help you for your homework tonight, because I want you to put these in a flow chart. So I try to put these in an order that would help you with your flow chart. All right. Now, I'm going to show this one I had done with an earlier class. Again, do I have all the same pieces? All the same pieces are there, but is the order scrambled? Yeah. Again, some of the main things are the same, but then you also notice, like when we did the triangle congruency statements, they were slightly different, right? But that's because however you listed the first one, you had to make sure they were in a corresponding order to write the second one. All right? So again, they can be slightly different, but still prove the same thing. All right. Any questions on that one? All right. Then let's take a look at the one that's slightly harder. So now, for this one, right, you guys already said that you thought this was the harder one, and it is. What do you think we could try and prove on this one? And let's just go with triangles. What two triangles do you think are congruent here? What was it? I heard some. All right, no, I like it. So AFD, BCE. That'd be perfect. And I think that those are the two that are going to be the easiest to prove congruent here. All right. So on here, I'm going to go ahead and write that down. The statement we're trying to prove, we said triangle AFD is congruent to triangle BCE. BCE. All right, so now, for this one, what things are given? So there's a lot of givens here. 9A, F, B. They're not equal. They are, what is that symbol? Parallel. AF is parallel to BE. Again, they're segments, so I want to make sure I use the segment notation over top of them. Yep. All right, so DA and BC, same thing. So AD is parallel to BC. What else do we know?
FE.
All right, FE is congruent to DC. Now, we have all our givens, we have our proof. So, again, doing a flowchart proof. Sorry, not a flowchart, a two-column proof. Your assignment tonight will be to turn it into a flowchart. We have our statements. We have our reasons. So let's start with the first given. All right. It doesn't really matter which one you start with, but I'm just going to start with the first one. So we have AF is parallel to BE. Why? Given. We were told that to start the problem. All right. Does this tell us any other information? So we have AF and BE. Should parallel lines tell us some type of information? So we had a section all about parallel lines, right? What types of things did we know when we had parallel lines? Did parallel lines tell us that segments were congruent? No. What did parallel lines usually tell us? If I drew two parallel lines and threw a transversal on there, what types of things did we know? We knew a whole bunch of angles were congruent, right? Again, that's only true if we had parallel lines. So on this diagram, we have parallel lines. What angles, so based off these two that we just said are parallel, which two angles do you think should be marked as congruent? AD. Well, angles. Angles. F and C? F and E. Okay. F and E. So you want this angle and this angle, correct? All right, I agree with that. However, one of those can't just use a letter. Which one can't we just use one letter for? E. Because there's more than one angle coming off of E. So we can say angle F. I'm fine with that. But angle F is congruent to angle what? GED. That works. GED works.
Where's the G?
So GED, or you could have said BED or BEC. Again, there's more than one way to name that same angle. So as long as E's the one in the middle and you use one of those points from each of the sides, that's fine. So I'm going to go GED. What type of angles are they? How did you know they are congruent? We have parallel lines, but what type of angles on those parallel lines? We had lots of different types of angles. Were they alternate interior angles? They are on the same side, but they're not same side interior, no. Corresponding. They're in the exact same position. So again, that's when we talk about corresponding. Same position is corresponding. Corresponding angle theorem. All right. So now that we have that, that's going to be it for that first given. All right. We have a second given, though, that also deals with parallel lines. So AD is parallel to BC. Why? Well, it was given. Good. Now, looking at that set of lines, is there something we can mark as congruent because of those? So kind of the same idea as what we just did before, right? So which two are they? C and D. Now, same thing that I said last time. For C and D, one of those, we can't just use one letter. C, I'm fine with using one letter, but D has multiple angles. So I'm going to use, let's do GDE. So now we're talking about that angle. And the reason again would be they're in the same position again. So it's again corresponding angle theorem. All right. The last part of this one is what makes this one a little more challenging, because there's something here that when we look at this, we know it has to be congruent. But the idea of figuring out how goes all the way back to like the very first chapter. So on here, we have two segments marked as congruent, right? That's our last given statement. So we're going to have to do something with that statement where we had these two were congruent. So I'm going to go ahead and write FE is congruent to DC. That's our last given. Now, this is the part that makes this one a little challenging. We need that third side of each of those triangles. So the third side of this the third piece for this triangle is the side FD. The third piece that we need for this triangle would be EC. If we could use those two pieces, then we could easily prove this because we have two angles and included side. But again, we don't have the whole side marked as congruent. We just have part of it. So can you guys throw out any ideas as to how we may be able to say that DF and EC are congruent? What do you think? Is there any ideas from earlier in the year? Okay, so they overlap. So they share a common part. So we do know that this piece is congruent to itself. All right, I agree with that. Now, we're not going to have to state that in order to finish this proof, but I like the idea that you recognize this piece is in both, right? Because we do have to use that idea that's in both. We don't have to necessarily list that as a part. We could. Anything else? What you got? It is something with segments. So here, let's cover up this piece so you can focus on that triangle. What piece do we need from this triangle right now? The bottom. What is the bottom? All right, well, the bottom, it is, but so this piece is what we need. We only have this piece right now. So this is the challenging part. Again, all right, we have that little pieces in both. Yes? If I add that to this, would we get FD? All right. So what is that called when we add those two pieces together? Addition, okay. So what was that? Segment addition. All right. So we're going to have to use segment addition on this one. That goes all the way back to chapter 1, right? If we add this plus this, then we get this. Same thing over here. If we add this plus this, then we get that piece. So we're going to have to use some segment addition here as well. All right. There's a couple different properties that we can use. So if we're doing segment addition, though, are we going to be using congruent symbols? Or are we going to be using equal signs when we do segment addition? An equal sign. So the next step, I'm actually going to go ahead and change this so that this is written as an equal statement. All right. What allows me to change this to an equal statement? So FE is equal to CD. So now I'm saying those lengths are equal. Well, we're going to be doing a lot with equality, but that's not what's letting me change it. So I went from a congruent symbol to an equal sign. What allows me to say that if I have two congruent segments, then the length of those segments are equal. Now we're digging up some old ideas here. If you have two congruent segments, what allows you to change between a congruent symbol and equal sign? If things are congruent, then their measures must be equal. Definition of congruency, or you could say definition of congruent segments. Either one works. But that's what allows us to change back and forth. So definition of congruent. Oops, I just misspelled congruent. Left out the U. Congruent segments. Again, if you just want to say of congruency, that'd be fine as well. So let me scoot this up. Now, all right. From here, we said that we needed to include this part EF, right? So I could add this EF to both of those. Yes? Do you agree with that? So I know that FE plus ED would be equal to ED. Whoops. Sorry. I wrote that poorly. Actually, let me write it in the same order. DC plus ED. Alright. Yeah. ED, not EC. Alright. I added ED to both sides. What property allows me to add something to both sides? This is going back quite a ways. This is like from one of our first proofs that we ever did. So we're not actually doing angle addition just yet. Here, sorry, not segment addition just yet. Here I just added the same piece, the same length to both sides. So if you add the same value to both sides of your equation, this has to do with balancing equations. So if you add the same value to both sides, that's called addition, property of equality. All right. Now, we want this to become FD, right? This is where we have to introduce our idea of the segment addition. So, FE plus ED would give us, FD. DC plus ED would give us CE. Is that time? All right. Segment addition. Yeah, I'm going to post this as well. All right. Yep. Now, there's only a couple of steps left. How much time do we actually have? 2 minutes. I might actually be able to finish this. So it's fine if you're packing up, but let me see if I can finish these last couple statements. All right. So we have this statement, and we have this statement. So we know that this whole thing is equal to FD. So you can replace that value. You're replacing the entire side of an equation with FD. We're also can replace the entire other side of the equation with CE. What do we call it when it's not just substitution, not just replacing one value, but replacing the entire side of the equation? Start with a T. Transitive property of equality. Now, again, we have basically what we need, but this says equals. We need it to be a congruency statement. So just like we did earlier, we changed from congruent to equal. We need to change it back to congruent using the same idea, definition of congruent segments, or if you just want to say of congruency, that's fine. And now we have three parts. We already knew at the beginning, we already knew early on it was ASA. Now we can actually say ASA and say the triangles are congruent. So triangle AFD is congruent to triangle BCE. All right. I will post that to Edsby. I want you to make this into a flow chart for homework.